Between the stars, in the deepest black, entire worlds may be drifting alone. No sunrise, no home star, no bright path around anything at all. Just planets, possibly billions or even more of them, moving through the dark like invisible castaways. That idea matters because it changes what a planet can be. By the end of this, you are going to understand how worlds can be born, stolen, or thrown into interstellar night. How scientists even suspect they are out there when they are so hard to see. And why rogue planets may be one of the strangest and most revealing populations in the galaxy. And if you enjoy space stories like this, where the universe turns out to be even weirder than it first looked, give the video a like and subscribe. It really does help, but only if this is your kind of thing. And down in the comments, want to tell me where you are watching from, and answer this. If you had to choose, would you rather stand under the sky of a rogue planet lit only by the Milky Way, or on a normal world with a bright sun? Now imagine the view changing. The stars of the galaxy are still there, spread out like frozen sparks, but one world after another has slipped free of their light and disappeared into the black. How do you lose a planet? How can something as large as a world become almost undetectable? Could there be more planets wandering the galaxy than planets orbiting stars? And if one of those dark worlds passed through our cosmic neighborhood, would we even notice before it was gone? To understand rogue planets, it helps to begin with the picture most of us already carry around in our heads. A star forms from a collapsing cloud of gas and dust, and around that young star, a spinning disk of leftover material flattens out, and inside that disk, grains become pebbles, pebbles become rocks, rocks become planetesimals, and over immense spans of time, some of those bodies grow into planets. That is the familiar version. It is tidy, almost comforting. Stars in the center, planets obediently circling them, moons around planets, all of it moving in patterns we can draw. Our own solar system seems to fit that picture well enough. The sun anchors everything. Mercury races close in. Jupiter dominates the outer system. Neptune sweeps through deep cold, far from the sunlight we know. Even the dwarf planets and icy bodies at the edge still belong to the sun. Their orbits may be stretched and tilted and strange, but they are part of a family. Rogue planets challenge that family portrait. A rogue planet, also called a free-floating planet or interstellar planet, is exactly what it sounds like. A planetary-mass object that does not orbit a star. It moves through space on its own, bound not to a sun, but only to the wider gravity of the galaxy itself. It is not merely far from a star. It is not on a very long orbit that takes thousands of years. It is effectively homeless. And the first shock is this. Rogue planets are not just a science fiction idea. Astronomers have strong reasons to think they exist, and in some cases, they have found candidates that are very likely real examples. That alone is strange enough, but the deeper you go, the stranger it gets. Because once you ask where rogue planets come from, and you discover that there may be more than one answer. Some may begin life in ordinary planetary systems and then get violently ejected. Others may form more like stars do, directly out of collapsing clouds, but never gather enough mass to ignite nuclear fusion. So when we talk about rogue planets, we are not talking about a single simple category. We are talking about an entire shadow population of worlds with different origins, different histories, and perhaps radically different conditions. Let us start with the most intuitive path into darkness: planetary exile. Young planetary systems are messy places. The neat diagrams in textbooks can make them look orderly, but the real early history of a solar system is often closer to a demolition site. Giant planets form. Smaller worlds emerge. Leftover debris flies everywhere, and gravity pulls and perturbs and amplifies tiny differences in motion until some objects settle into stable orbits and others do not. When multiple large planets interact, especially gas giants, the result can be chaotic. One massive world tugs on another. Orbits stretch. Encounters become closer. Angular momentum gets traded around like currency in a crowded market. Eventually, one object may be kicked inward, one outward, and one may receive enough energy to escape the star entirely. That is the essential mechanism. A planet can be thrown out. It sounds extreme, but in celestial mechanics, extreme is often just what happens when gravity is given enough time. A planetary system is not a machine built to remain balanced forever. It is a gravitational negotiation. And early on, some participants lose badly. There is evidence that this kind of instability happens. Astronomers have found exoplanet systems with giant planets on very elongated, eccentric orbits, or in arrangements that suggest past upheaval. We have strong reasons to believe that migration, close encounters, and orbital scattering are common in young systems. In our own solar system, the giant planets almost certainly moved from where they originally formed. The history is still debated in its details, but the broad story is not one of perfect stillness. It is one of change, rearrangement, and dynamical conflict. In some simulations of planetary formation, ejections are not rare accidents. They are expected outcomes. Especially when giant planets are involved, smaller bodies can be scattered like loose stones from a spinning wheel. Some of those bodies fall into the star. Some collide with other planets. Some end up on distant, stretched-out orbits. And some leave forever. Picture a newborn planetary system a few million years old. The star is young and angry, shedding radiation and stellar wind. The gas disk has not completely vanished. Several giant worlds are still moving through it, nudging and disrupting each other. One close encounter changes everything. A planet dives past a more massive neighbor, steals a little orbital energy. Then another encounter sharpens the effect. Suddenly, its path is no longer a long ellipse around the star. It is open. The planet is no longer falling around its sun. It is leaving it. At first, it still glows with leftover heat from formation. Behind it, the star shrinks. The sky loses its brightest anchor. The warmth fades, then plunges. Any atmosphere begins to respond. Surface chemistry changes. If there were moons, some may be stripped away, though a few might remain. If there were oceans on the surface, they begin to freeze from the top down. The planet enters a kind of cosmic afterlife, no longer dead exactly, but severed from the source of energy that once defined its environment. And that may happen again and again across the galaxy. Our Milky Way contains hundreds of billions of stars. Around many of them, planets form. If even a modest fraction of planetary systems eject one or more worlds during their early violence, the number of free-floating planets could be enormous. There was a time when some estimates hinted there might be as many rogue planets as stars, or even more. Those early numbers generated a lot of excitement, although later work has made the picture more cautious and nuanced. The true number is still uncertain. It depends on how often planets are ejected, what masses they have, how we define the category, and how incomplete our observations still are. But uncertainty here does not mean insignificance. It means the galaxy may be hiding a population we have only barely begun to detect. And then there is the second pathway, the one that blurs the line between planets and stars. Not every rogue planetary mass object must have been thrown out of a planetary system. Some may form on their own in giant molecular clouds, the cold, star-forming nurseries where new suns are born. If a clump of gas and dust collapses under gravity, but does not gather enough mass to ignite sustained hydrogen fusion, it will not become a proper star. Depending on its mass, it may become a brown dwarf, which is often described as a failed star. Though that phrase is a bit unfair, brown dwarfs are real objects with their own physics and personalities, glowing faintly from contraction, and in some cases briefly fusing deuterium early in life. Below a certain mass threshold, even that limited fusion does not happen. Now you have something with planetary mass but star-like formation history. Is it a planet? Is it a sub-brown dwarf? Is it a free-floating planetary mass object? The labels start to wobble. This is one of the reasons rogue planets are scientifically tricky. There are at least two ways to classify an object: by how massive it is and by how it formed. If you focus on mass, then anything in the planetary range might count. If you focus on origin, then an ejected world and a star-like collapse object are not the same kind of thing, even if they have similar masses. Nature, as usual, is less interested in our categories than we are. Still, for the viewer standing at the window of this idea, the distinction matters because it tells us what these objects can teach us. An ejected planet tells us about the violence of planetary systems. A directly formed, free-floating planetary mass object tells us about how fragmentation works in star-forming clouds and about the lower limits of object formation in the galaxy. Both are fascinating. Both are part of the story, but they are not identical stories. So how do you find a world that emits little or no light and circles no star? This is where astronomy becomes wonderfully indirect, and much of modern space science is the art of seeing the invisible by its effects. If a rogue planet is young and still warm from formation, it may glow faintly in infrared light, not bright enough to stand out easily against the universe, but enough for sensitive telescopes to detect under the right conditions. Infrared is the band of heat, the light of warm objects that are not hot enough to shine brilliantly in visible wavelengths. Newly formed giant rogue planets, especially ones with several times Jupiter's mass, can be easier to spot this way because they still carry internal heat like cosmic embers. Astronomers have indeed found free-floating planetary mass candidates in young star-forming regions using infrared observations, in places like the Orion Nebula cluster, where stars and substellar objects are young, warm, and comparatively nearby in galactic terms. Surveys have identified isolated objects in the planetary mass range. These discoveries are compelling, but they also come with classification challenges. Estimating mass depends on age and models of how such objects cool. Young objects are brighter, old ones dimmer. A slightly wrong age estimate can shift an object across a category boundary. So scientists proceed carefully. Then there is microlensing, one of the most elegant methods in astronomy. According to general relativity, mass bends space-time, and light follows that bending. If a foreground object passes almost exactly in front of a background star from our point of view, the foreground object's gravity can act like a lens, briefly magnifying the background star's light. We may not see the lensing object itself at all, or we see the background star brighten in a distinctive pattern. This is gravitational microlensing. It is rare because the alignment has to be just right. It is temporary because everything is moving. And it is powerful because it can reveal otherwise dark objects. For stars, microlensing events can last much longer. For planetary mass objects, the events can be very short, sometimes lasting only hours or a couple of days, depending on the mass and geometry. That means astronomers must monitor huge numbers of stars continuously, looking for tiny changes and catching them in time. It is like trying to detect a single brief glint in a city full of windows, except the city is the Milky Way. This technique has produced some of the most tantalizing evidence for rogue planets. Surveys have reported short-duration microlensing events consistent with planetary-mass lenses that do not appear to be bound to visible stars. In some cases, the signal strongly suggests a free-floating object, though it can be difficult to rule out every alternative, such as a planet on a very wide orbit around a dim host star. In science, likely rogue planet often means the best current interpretation given the data, not case closed forever. Still, with enough events and enough statistical analysis, a picture begins to emerge. And that picture suggests that the galaxy is not empty between stars. It is occupied by faint bodies, many of them too dark and cold to see directly, whose existence becomes visible only for a moment when gravity betrays them. That is a beautiful sentence in itself. Gravity betrays them. Imagine a background star tens of thousands of light years away toward the crowded center of the galaxy. Night after night, telescopes watch it. Then, for a few hours, the star brightens, not because the star changed, but because some invisible object crossed the line of sight and warped space just enough to focus its light toward us. The signal rises and falls. The invisible traveler continues on. If the lensing object is a rogue planet, then we may have caught one of the loneliest worlds in the galaxy, doing the only thing that made it briefly findable. There are also possibilities for detecting rogue planets by their residual heat, by direct imaging in especially favorable cases, and perhaps in the future, by even more sensitive wide-area surveys. But at present, the reality is sobering. These objects are hard to find, extremely hard, which means whatever we have already glimpsed is probably a small fraction of what is actually out there. That observational difficulty shapes everything. If rogue planets are mostly cold, old, and isolated, then the galaxy could be full of them, and we would still miss most of them. A bright star announces itself across enormous distance. A dark planet does not. A planet without a host star is, in a sense, trying very hard not to be seen. Now let us step away from detection and ask the question that gives rogue planets so much emotional weight. What would one actually be like? The answer depends completely on its mass, age, composition, and history. There is no single rogue planet environment. Some may be gas giants larger than Jupiter, wrapped in dense atmospheres and still glowing faintly with internal heat. Some may be icy terrestrial worlds, small rocky planets frozen solid after exile. Some may have moons. Some may once have had oceans and skies. Some may never have known sunlight at all if they formed independently in darkness. A young gas giant rogue planet could be unexpectedly dramatic. Fresh from formation, such a world might radiate enough heat to glow dull red in infrared if your eyes could see that way. Thick clouds may churn in its atmosphere. Weather systems could rage across vast layers of gas. In visible light, it would appear almost black, perhaps with only the faintest trace of reflected starlight, if any nearby stars happened to shine on it. But in thermal imaging, it might look alive, a self-warmed storm world adrift in the void. As time passes, though, the heat leaks away. Planets are not stars. They do not have sustained fusion to keep them warm. They cool. A rogue gas giant billions of years old would become colder and dimmer, settling toward temperatures so low that its atmosphere and cloud chemistry would shift into exotic states. Depending on the temperature and pressure, clouds of water, ammonia, or other compounds might form at different depths. The world would still have weather, still have internal structure, perhaps still have a warm core, but its visible face to the universe would be almost nothing. A rocky rogue planet is perhaps even more haunting. Remove Earth from the sun, and the first thing to understand is that the surface would not stay habitable for long, and sunlight is the main energy input driving our climate. Without it, surface temperatures would crash. Oceans would freeze on top. The atmosphere would condense and transform. Within a relatively short astronomical time, the surface would become lethally cold. But this is where a simple picture becomes more interesting. Even without sunlight, a planet is not always uniformly dead. Internal heat matters. Earth has geothermal energy, generated by leftover heat from formation and by radioactive decay inside the planet. It is small compared with the energy we receive from the sun, but it is not zero. If Earth were somehow ejected into interstellar space, the surface would freeze, yes. But beneath the ice, especially under a thick enough insulating layer, liquid water might persist for a very long time in subsurface oceans. Or hydrothermal systems might still exist on the ocean floor. Chemical energy gradients would remain. If life had already emerged before the ejection, some microbial ecosystems might survive in hidden habitats for immense timescales. This idea has fascinated scientists for good reason. Habitability is usually tied to the so-called habitable zone, the range of distances from a star where liquid water could exist on a planet's surface. Rogue planets blow a hole in that neat concept. They suggest that if a planet has sufficient internal heat, a thick atmosphere, an insulating ice shell, or tidal heating from a moon, then liquid water and potentially life-supporting environments could exist far outside any classic habitable zone. Not comfortably, not on the surface under blue skies, but perhaps in darkness below. There have been scientific studies exploring whether free-floating planets with thick hydrogen atmospheres might retain enough heat to keep surface water liquid, at least in some cases. The basic logic is that hydrogen under high pressure can become an effective greenhouse gas through collision-induced absorption. In plain language, a thick hydrogen blanket might trap geothermal heat far better than you would expect. Under the right circumstances, a planet drifting between stars could remain surprisingly temperate at the surface or just below it. This is not a claim that rogue planets are likely garden worlds. That would be going too far. The conditions required are specific, and we do not know how common they are. Such planets would also face enormous challenges: atmospheric retention, geological history, an initial composition, long-term stability, and more. But the mere fact that serious science has explored the possibility tells you how radical the implications are. Life, if it exists beyond Earth, may not need a star in quite the way we once assumed. Even if the surface is frozen solid, subsurface habitability remains plausible on some rogue worlds. In our own solar system, moons like Europa and Enceladus already hint at this possibility. They orbit a star, yes, but their subsurface oceans are maintained largely by internal and tidal heating rather than direct sunlight. If such environments can exist here, then perhaps a rogue planet with enough internal heat and enough insulation could host a hidden ocean in total darkness. Picture a frozen crust miles thick, harder than rock in the deep cold of interstellar space. Above it, endless black, no dawn, no sunset, only distant stars, unnaturally sharp in a sky with no airglow and no sunlit horizon. But far below, beneath the pressure of ice and the warmth rising from the planet's interior, water remains liquid. Mineral-rich vents leak heat into the dark sea. Chemical reactions continue. If life can live around hydrothermal systems on Earth without sunlight, then the universe may not care very much whether a world has a sunrise. That is one of the profound shifts rogue planets introduce. They make the cosmos seem less dependent on the familiar script. Of course, many rogue planets would be utterly sterile, frigid, dark, and chemically uneventful on any human scale. But even a sterile rogue planet is astonishing. It is a world-sized object carrying a history. It may have clouds, ice layers, magnetic fields, moons, core dynamics, frozen atmospheres, or buried oceans. It may be older than Earth. It may have once orbited a star that no longer even exists. It may have wandered the galaxy for billions of years, crossing spiral arms, passing through interstellar clouds, and never once settling into the warmth of a sun. And now let us talk about the danger. Not because rogue planets are a hidden menace lurking behind every star. They are not. Space is far too vast for that kind of cinematic chaos to be common. But in principle, a large unseen mass moving through a planetary system could cause serious disruption. If a rogue planet passed through the outer reaches of a star system, its gravity could perturb comet reservoirs, alter distant orbits, or in extreme close cases, destabilize planets. The odds of a direct collision with a planet are extraordinarily low. The galaxy is mostly emptiness, but low probability is not zero, especially over billions of years and hundreds of billions of stars. There is a broader version of this idea that astronomers consider in many contexts. Planetary systems are not isolated in a perfect vacuum. They exist in a galaxy full of passing stars, molecular clouds, and perhaps free-floating worlds. Over long enough timescales, gravitational encounters happen. Most are distant and mild. A few may leave lasting marks. In our own solar system, there has long been scientific interest in whether past stellar flybys have influenced the far outer regions, such as the Oort cloud. A rogue planet passing close enough could in theory do something similar, though evidence for any specific past rogue planet encounter in our system is lacking. And this is an area where imagination can run much faster than evidence, so it is important to stay grounded. The possibility exists in the laws of physics. The historical proof in our case does not. Still, let the scale of that possibility settle in. There may be unseen worlds moving through the galaxy, each one carrying enough gravity to reshape smaller bodies if it comes near enough. Most will never approach us. Most will remain forever unknown. But the galaxy is not a static map of glowing suns. It is a dynamic environment full of moving masses, some bright, some dark. That matters for another reason too. It changes how we think about the census of worlds. For most of human history, planets were the things we could see wandering across our own sky. Then planets became the family of the solar system. Then, with the exoplanet revolution, planets became a common feature of stars throughout the galaxy. Thousands have now been detected, and we know that planets are not rare exceptions. They are part of the standard architecture of nature. Rogue planets suggest the count may be even larger than that revolution first implied. If many worlds are untethered, then a star count is not enough to estimate the number of planetary environments in the galaxy. The Milky Way may contain a hidden surplus of worlds that belong to no sun at all. And that brings us to one of the most intriguing numerical questions in astronomy. How many rogue planets are there? The honest answer is that we do not know yet. Estimates have varied widely. Early microlensing interpretations once suggested there could be nearly 2 Jupiter-mass rogues for every main sequence star, which, if true, would have implied a startling abundance of giant, free-floating planets. Later observations and analyses have challenged such high numbers, especially for Jupiter-mass objects. More recent results often point toward a more moderate population, though still potentially substantial. There is also reason to think lower-mass rogue planets, including Earth mass or smaller bodies, could be more numerous, but even harder to detect. That last part is crucial. Detection biases distort our view. A massive, warm, rogue planet is easier to detect than a small, cold one. So if we find some large examples, that does not mean they dominate the true population. It may simply mean our instruments are catching the easy cases first. Astronomy often begins by discovering the loudest members of a hidden population and then slowly working down toward the quiet majority. It is a little like standing on a dark shoreline at night and concluding only big ships exist because they are the only lights you can see offshore. The ocean may be full of smaller vessels with their lights off. Rogue planets are like that. The darkness hides the count. The coming years may improve the situation dramatically. More powerful infrared observatories, more sensitive wide-field surveys, and space telescopes designed to detect microlensing events could greatly expand the sample of known free-floating planetary-mass objects. The Nancy Grace Roman Space Telescope, for example, is expected to be extremely powerful for microlensing studies and may help constrain the population of rogue planets down to much lower masses than current surveys can easily reach. If those observations succeed, we may go from guessing at a hidden population to actually mapping part of it. That could be one of the next major shifts in planetary science. Not just finding more exoplanets around stars, but uncovering entire classes of worlds that orbit nothing at all. There is another layer to the mystery that makes rogue planets emotionally gripping in a way that numbers alone cannot. A normal planet has a relationship. It has a sun. It has seasons or day-night cycles, or at least some regularity defined by a star. A rogue planet has none of that. Its sky would be a lesson in absence. If you stood on the surface of a frozen, rogue, Earth-like world, if such a thing existed, and if you could survive long enough to look up, the stars would be extraordinary. Without a nearby sun, the sky would be permanently night. The Milky Way might arch overhead with terrifying clarity. Bright planets would not move among the constellations because there would be no local planetary family to see. There would be no blue daytime, no sunrise line, no golden afternoon. Time itself might feel broken. Human intuition is built around cycles of light. On a rogue world, that rhythm vanishes. Even weather, if present, would be strange. On a gas-giant rogue planet, internal heat might drive storms from below rather than sunlight from above. On a frozen, rocky rogue, surface changes might be governed mostly by slow geology, cryovolcanism, if any, or occasional impacts. If the atmosphere had mostly collapsed onto the surface as ice, the sky might be almost airless. If a thick atmosphere remained, it could create pressure, haze, and a dim glow of thermal processes unlike anything familiar. And then there is the question of moons. A rogue planet could carry its own miniature system into exile. If a giant planet were ejected, some moons might remain bound to it. In that case, you do not just have one world drifting through darkness. You have a whole dark archipelago, a planet and its attendants wandering the galaxy together. Tidal forces between the planet and moon could even help keep internal heating active, especially for the moon. In principle, a moon around a rogue gas giant could be one of the more plausible havens for subsurface or even surface liquid water under special conditions. Again, this is not to say such inhabited dark moons are expected. It is to say the possibility space is wider than the old textbooks suggested. The universe is under no obligation to keep habitable environments only where they are visually convenient. Sometimes the most important scientific ideas are not the ones that tell us exactly what exists. They are the ones that break a hidden assumption. Rogue planets break several. They break the assumption that planets are always defined by stars. They break the assumption that darkness means inactivity. They break the assumption that a world without sunlight is automatically irrelevant. And perhaps most of all, they break the assumption that what we can easily see is a fair measure of what is really there. Astronomy keeps teaching that lesson. The visible universe is not the whole universe. Most matter is dark matter, though not in the planetary sense. Most of the atoms between stars are spread thin and hard to notice, and black holes announce themselves mainly by effects. Neutron stars can be tiny and deadly. Exoplanets were hidden from us until recently, not because they were rare, but because they were difficult to detect. Rogue planets fit that tradition perfectly. They may be common, not in spite of being hard to see, but partly because the universe produces more hidden things than bright ones. There is a poetic irony in this. For thousands of years, human beings understood planets as wandering lights in the sky. The word itself goes back to that idea, the wanderers. And now, after centuries of astronomy refined the concept into worlds orbiting stars, we are discovering that some planets may be true wanderers after all. not wandering against the backdrop of stars from night to night as seen from Earth, but wandering physically through the galaxy, undetached and silent. The old meaning comes back in a deeper form. Let us linger for a moment on what the journey of one rogue planet might be. Imagine a world forming around a young star in a busy stellar nursery. Its system contains several giant planets. The star is one of many, born in a cluster where nearby suns glow through gas and dust. The rogue planet begins as just another member of that system, perhaps a large icy world beyond the snow line where volatiles are abundant. For a few million years it circles its star under dim, distant light. Then migration starts. A gas giant moves inward. Resonances build, orbits cross. One catastrophic close encounter later, the smaller world is accelerated past escape velocity. At first, the planet is still in the neighborhood of its birth. The cluster around it is full of young stars. Nearby, suns still offer some distant illumination. But the cluster itself gradually disperses over time. The ejected planet does not remain part of any local family. It enters galactic orbit, circling the center of the Milky Way over hundreds of millions of years. Spiral arms drift. Supernovae explode far away. Interstellar clouds loom and recede. The planet crosses regions of different stellar density, perhaps passes relatively near stars that never capture it, perhaps glides through darkness so complete that no human imagination can comfortably picture it. If it has a moon, they remain together, locked in mutual gravity. If it has internal heat, that heat slowly declines. If it once had an atmosphere, the chemistry evolves. If it ever hosted life beneath ice, that life adapts or dies according to conditions we can only model imperfectly. Through it all, the planet has no dawn. It does not belong to any sunrise. Billions of years later, an alien civilization or a future human instrument catches it for a moment, not by seeing the world itself, but by watching a distant star blink brighter. A gravity signature, a brief clue. The whole long journey reduced to a few hours of data. That is how much of the universe reaches us, not as a full picture, but as a hint. Now, because this topic sits right on the edge between known science and tempting speculation, it is worth being very clear about what scientists know and what they do not. We know planets can be gravitationally ejected from planetary systems. The physics is straightforward, and simulations show it happening readily under the right conditions. We know there exist isolated objects with masses in the planetary range, especially in young star-forming regions, though pinning down their exact origins can be difficult. We know microlensing has revealed short-duration events consistent with free-floating planetary-mass objects. We know giant planets and smaller worlds should both, in principle, be able to exist without host stars. We do not yet know the true abundance of rogue planets across all masses. We do not yet know what fraction formed by ejection versus direct collapse. We do not know how many retain thick atmospheres, subsurface oceans, moons, or any conditions remotely suitable for life, and we certainly do not know of any inhabited rogue world. Those limits matter. The mystery is real, but so is the uncertainty. Good astronomy lives in both. In some ways, rogue planets are part of a broader modern realization that planetary systems are not neat clockwork displays, but dynamic evolutionary stories. Consider what we have learned from exoplanets in general. Hot Jupiters orbit scorchingly close to their stars, where no one expected giant planets to form. Super-Earths, a class absent from our own solar system, seem common elsewhere. Worlds orbit binary stars. Systems are packed in resonant chains. Orbits tilt, migrate, destabilize, and settle. Every decade has made the galaxy less like our childhood diagrams and more like a wild experiment in gravitational architecture. Rogue planets are a natural extension of that chaos. If systems can build, move, and scramble planets, then some planets will get thrown away. The surprise is not that rogue planets should exist. The surprise is that our older mental picture left so little room for them. There is also a sobering philosophical edge here. On Earth, exile is a deeply human idea. To be cast out, cut off, and sent into the cold beyond the boundary of the known. Rogue planets are not conscious, of course. They do not feel loneliness. But the metaphor persists because their situation is so starkly legible to us. A world without a sun feels like a sentence. And yet, the scientific reality may be more interesting than the metaphor. Some rogue planets may not be tragic ruins. Some may be stable, internally active, even in a strange way self-contained. They do not need sunlight to exist as worlds. They only need enough mass, composition, and history to continue being physically complex. From that perspective, rogue planets are not failed planets. They are planets living by a different rulebook. That shift in perspective matters because astronomy is full of objects once described mainly by what they are not. Brown dwarfs as failed stars, Pluto as not a major planet, rogue planets as not orbiting anything. But nature is richer than those absences. A brown dwarf is a real type of world. A dwarf planet is a real category of body. A rogue planet is not merely a missing solar system member. It is its own kind of environment. Consider temperature in deep space. Far from any star, an exposed object tends toward equilibrium with the background radiation field and whatever internal heat it retains. The cosmic microwave background itself is only a few degrees above absolute zero. That number is almost absurdly low by human standards. It is the afterglow of the Big Bang, filling all of space with faint microwave radiation. Against that backdrop, a rogue planet can still be relatively warm inside, because internal heat leaks outward slowly. If the planet is large and wrapped in insulating layers, the difference between the frozen exterior and the deeper interior can be enormous. The outer face may be a tomb. The inside may still be geologically alive. This layered reality appears again and again in planetary science. What looks dead from space can be active below. Mars looks dry, yet preserves evidence of ancient water and still has subsurface questions. Europa looks like a bright ice ball, yet likely hides an ocean. Titan looks dim and frigid, yet hosts lakes and weather made of methane. Rogue planets push that lesson to the extreme. The darkest worlds may still have interiors with chemistry, heat flow, and structure worth studying. And if future astronomy becomes ambitious enough, rogue planets may even become destinations of extraordinary scientific interest. This sounds far off, and it is. But imagine a nearby rogue planet detected through infrared emission or microlensing combined with follow-up measurements. If it passed within a few light years, it could become one of the most reachable extrasolar worlds, because unlike planets deep inside other star systems, it would not be trapped in the glare of a host star. A probe sent over centuries by a future civilization could in principle study it directly. No stellar radiation pressure to contend with. No deep gravity well near a star. Just a dark target drifting through interstellar space. That does not make it easy. Reachable in interstellar terms still means staggeringly difficult. Ein, but conceptually, a rogue planet is one of the few kinds of extrasolar world that might one day be visited without first crossing the obstacle course of an alien solar system. There is even an even stranger possibility. A rogue planet passing through interstellar space could occasionally pass close to a star and be temporarily illuminated from afar, or in rare cases, perhaps even gravitationally captured under special circumstances, though true capture without energy loss is difficult and uncommon. More often, it would simply continue past, an interstellar traveler briefly entering another system's outskirts before leaving again. A sun it never belonged to might rise in its sky for a geologically insignificant moment, then fade. Imagine a frozen world wandering for 2 billion years in darkness, or then drifting through the far edge of another stellar system. Its surface, locked in deep cold, receives a feeble new glow. Comets nearby change course. Maybe its upper atmosphere responds. Maybe nothing much happens. Then it moves on. Even in the galaxy, there are fleeting encounters. If all this feels cinematic, that is because the actual physics is cinematic. Gravity, exile, dark oceans, silent skies, hidden populations, brief detections. None of it needs embellishment. But we should also ask a practical question. Could a rogue planet be anywhere near us? There is no evidence for a known rogue planet currently passing dangerously close to the solar system. Objects in the outer solar system and the interstellar neighborhood are studied intensely, and while there are many open questions about distant small bodies and possible undiscovered planets bound to the Sun, that is a different issue from a truly rogue interstellar planet heading our way. If such a large object were nearby, its gravitational effects or faint heat signature might eventually reveal it depending on its mass and distance. The larger lesson is not immediate danger. It is humility. Our solar system lives inside a galaxy that contains many things we do not see directly. Most of them are harmlessly distant. Some are simply difficult to detect. The dark is not empty, and our confidence should always leave room for the undiscovered. There is a historical pattern here. Every time astronomy invents a better way of seeing, the universe gets busier. First, the naked eye saw stars and planets. Then telescopes revealed moons and rings, nebulae, galaxies. Then spectroscopy showed chemical composition. Radio astronomy uncovered invisible sources. X-ray and gamma-ray astronomy revealed violent events. Infrared telescopes opened dusty star nurseries and cool objects. Gravitational techniques found unseen mass. Exoplanet methods turned points of light into systems full of worlds. At no stage did the universe become simpler. It became more crowded, more layered, and less centered on our initial assumptions. Rogue planets fit that exact pattern. They are what emerge when you realize that planetary science does not stop at the edge of starlight. And perhaps that is the deepest conceptual shift of all. We are used to defining environments by their local star. But the galaxy itself is an environment. Interstellar space is not merely the gap between important places. It has magnetic fields, radiation, gas clouds, cosmic rays, gravitational tides, passing objects, and timescales so vast that even rare events accumulate. A rogue planet belongs to that environment the way an oceanic drifter belongs to the sea, not to any harbor. The analogy is imperfect, but useful. On Earth, a drifting iceberg or a long-lived buoy may move through currents, storms, and seasons, shaped by forces broader than any coastline. A rogue planet drifts through galactic structure, tracing a path determined by the Milky Way's mass distribution, its origin conditions, and every gravitational nudge it has received. It is not stationary in darkness. It is in motion inside a larger system. This also means rogue planets could preserve records of environments far from any sun. Their surfaces or atmospheres, if we could ever examine them closely, might tell us about cosmic rays, interstellar chemistry, long-term cooling, and planetary evolution without stellar energy input. They would be laboratories for understanding what happens to worlds when nearly all external warmth is removed. That is not a side note in planetary science. It is a fundamental test of how robust planets are as physical systems. And now consider the psychological effect of knowing these worlds may exist in huge numbers. It changes the emotional geography of the night sky. When you look up, you see stars because stars are bright. You do not see the dark bodies between them. But if rogue planets are common, then the apparent emptiness between those points of light is misleading. There may be worlds in that darkness right now, ancient and frozen, or massive and cloud-wrapped, or carrying hidden oceans under ice, not close enough to appear in our sky, not visible to the eye, but present. The night sky would still look the same, and yet your understanding of it would be fuller, denser, stranger. The gaps would no longer feel like nothing. They would feel inhabited by possibility. That is one of the great gifts of astronomy. It does not only tell you new facts, it changes what emptiness means. A century ago, planets around other stars were largely speculative. Today, we know they are everywhere. A few decades ago, brown dwarfs were uncertain. Now they are established. Rogue planets may be following a similar arc, moving from theoretical oddities to recognized members of the galactic population. The exact numbers will matter. The formation channels will matter. The boundary definitions will matter, but the broad lesson already stands. The universe makes worlds more freely than our first intuitions allowed. Some of them are warmed by suns. Some are trapped in tidal embraces. Some are scorched, some frozen, some inflated, some shattered, and some simply drift. When you think about it long enough, that last category may be the most haunting, because it removes the comforting center. Our minds like systems with anchors. A rogue planet has none that you can easily point to. Its history is still anchored in physics, of course, but visually, emotionally, cosmically, it is a world in the dark between households. And yet maybe that is why it matters so much. A rogue planet is a reminder that the universe is not built around what feels familiar. Stars are common, but they are not required for every planetary story. Light is precious, but it is not the only source of activity. Stability exists, but it is often born out of prior chaos, and the hidden can outnumber the obvious. In that sense, rogue planets are not just isolated curiosities. They are a lesson in cosmic realism. The galaxy is larger, less orderly, and more imaginative than the simplified maps in our heads. Worlds can be born in light and end in darkness. Worlds can form in darkness from the start. Worlds can survive conditions that would once have seemed disqualifying. And the line between barren, active, and potentially habitable may run through places we have barely begun to consider. There is something deeply human about being unsettled by that and thrilled by it at the same time. Because we live on a planet that belongs very clearly to a star. Our days, seasons, climate, biology, and history are written in sunlight. To discover that other worlds may wander the galaxy without any star at all is to realize that our own way of being a planet is only one version among many. Familiarity is local. Strangeness is universal. That may be the wider meaning of rogue planets. They remind us that the cosmos is not a sparse collection of bright islands separated by empty water. It is a layered, crowded, dynamic place in which much of the substance and story lies in the dark. Human knowledge advances by lighting up small parts of that darkness. One method, one observation, one clue at a time. And each time we do, the result is rarely a tidy simplification. More often, it is a deeper, richer complication. A planet without a sun would once have sounded like a contradiction. Now it sounds like a frontier. And there is a quiet dignity in that, in the possibility that somewhere between the stars, far beyond any warming dawn, a world is still turning, still cooling, still carrying a hidden interior, still following a path around the galaxy that no one would ever notice without a brief bend of light. It is not asking to be seen, but the universe has left us just enough clues to know it may be there. So the next time you look up at the night sky, remember that the stars are only the part that shines. Out in the black between them, entire worlds may be wandering unseen, ancient, cold, and astonishingly real. Thank you for watching, and if this journey into the dark held your attention, I am glad you came along.